Hi, in the textbook Linear Algebra and its Applications by David Lay, there are many true-false questions. We will give the answers for those questions. We use the fourth edition of this book. Today, you may find the new edition of this book. Questions in section 2.8, subspaces of Rn at page 151. Problem 21. A. A subspace of Rn is any set H such that 1. The zero vector is in H. 2. U, V, and U plus V are in H. And 3. C is a scalar, and Cu is in H. 4. A subspace of Rn is any set H of Rn such that 1. The zero vector is in H. 2. If UV in H, then U plus V in H. 3. If U in H and C is a scalar, then Cu in H. E. If V1 till Vp are in Rn, then span V1 till Vp is the same as the column space of the matrix V1 till Vp. 2. By the definition of the column space of a matrix A. 3. The set of all solutions of a system of m homogeneous equations in n unknowns is a subspace of Rm. 4. The set of all the solutions Ax equals 0, where A is a m times n matrix, is a subspace of Rn, not M. E. The columns of a invertible n times n matrix form a basis for Rn. 2. Since the matrix is invertible, the n columns form a linearly independent set. So the n columns form a basis of Rn. B. Row operations do not affect linear dependence relations among the columns of a matrix. 4. Elementary row operations do not affect linear dependence relations among the columns of a matrix. For the identity matrix 1, if every row multiplied by 0, then we get a matrix 0. All the columns become linearly dependent. So these row operations affect linear dependence relations among the columns of the identity matrix. Problem 22. A. A subset H of Rn is a subspace if the zero vector is in H. 4. Example, H is the set of 3 vectors, the zero vector in H. This vector plus this vector equals 1, 1 is not in H. So H is not a subspace. If B is an echelon form of a matrix A, then the pivot columns of B form a basis for column A. Fourth example, for the matrix A equals this one, we can verify these 3 columns are linearly dependent, and these 2 columns are linearly independent. So the column space of A is generated by these 2 vectors. Then by those elementary row operations, we get an echelon form of A. this and this are pivots. So these two columns are pivot columns of B. But the third row and the fourth row all 0. So these two columns cannot generate these two vectors. So the pivot columns of B do not form a basis for column space of A. See, given vectors V1 till Vp in Rn, the set of all linear combinations of these vectors is a subspace of Rn. 2. First of all, the zero vector is a linear combinations of this V1 till Bp. Then we can easily verify other properties. B. Let H be a subspace of Rn. If X is in H and Y is in Rn, then X plus Y is in H. For example, H is generated by this vector 0, 1. Then 0, 1 is in H and 1, 0 is in R2. But the sum of these two vectors equals 1, 1 is not in H. The column space of a matrix A is the set of solutions of AX equals B. For example, if B not 0, then the 0 vector is not in the set of solutions of AX equals B, but the 0 vector is in the column space of A. Questions in section 3.2. Properties of determinants at page 175. Here, in problems 27 and 28, A and B are n times n matrices. Problem 27. A. A row replacement operation does not affect the determinant of a matrix. For example, the identity matrix. If the first row was replaced by 330, then the determinant of this one equals 3, not 1. But an elementary row replacement operation does not affect the determinant of a matrix. B. The determinant of A is the product of the pivots in any echelon form U of A multiplied by -1 R, where R is the number of the row interchanges made during row reduction from A to U. Fourth example, this determinant of the matrix, this one is 0, not the product of the pivots 1, 1. C. If the columns of A are linearly dependent, then determinant A equals 0. 2. Since a n times n matrix is invertible if and only if its determinant not 0. B. Determinant A plus B equals determinant A plus determinant B. For example, determinant the sum of these two matrices is 0 because this matrix plus this matrix is a 0 matrix. But determinant of this matrix is 1. And the determinant of this matrix is also 1. So the sum of these two determinants is 2, not 0. Problem 28. A. If two row interchanges are made in succession, then the new determinant equals the old determinant. 2. Because two row interchanges are made in succession, made one row interchange, the determinant change sign, and made twice row interchanges, the new determinant equals -1 square, old determinant. The determinant of A is the product of the diagonal entries in A. 4. Example, the determinant of this matrix equals -1, and the product of the diagonal entries is 1 times 0 times 0 equals 0. 3. If determinant A is 0, then two rows or two columns are the same. O a row or a column is 0. 4. Example, the determinant of this matrix is 0. Two rows or two columns are not the same, and all rows or columns are not 0. B. Determinant A transpose equals minus determinant of A. 4. Because determinant A transpose equals determinant A. Thanks for watching. Bye.